Okay, so that link there in the chart, in the chat, has a chart on it. And at the bottom of that chart then has the practice test.
Okay,
And,
yeah, I see that.
okay,
Cool.
good. And that's what you can work on now this afternoon until I send more. That's one of the things I want to send out. Then also let me jump over. He has also done a test review. That's on the SBCC Physics YouTube channel. This is the channel I have my lectures, and the channel we used before this COVID hit. And when the COVID hit, I've been posting additional stuff like our labs and your video solutions all on my a different one. I kind of wonder if that was smart or not. But anyways, somewhere in here, let's see, exam reviews. Here we go. So if I hit playlist, then there's exam reviews. And there's number 1. And here's number 2. So what I'm going to do is put this also in the chat here. This link, if you click on it, will take you to that playlist that has all the exam reviews for this semester.
Okay, so let's get started.
Whoops, was that me or you, Jake? So you must have clicked on it. Okay, that sounded like Don. All right.
Sorry.
Right.
It works.
Good. And then, and I don't know if I can come up with it quickly enough. So maybe I will. Well, maybe I can. Let's go back to that playlist. Let me at least give it a try here. Because the third thing that I want to send you guys would be the video lectures you've been watching. That playlist is from spring of 2014. Yeah, here's that playlist. So each Sunday I send you the links from spring of 2014, but I experimented with recording the year before. So spring, if you go to the playlist for spring of 2013 and the Physics 123 lectures. Let me click on that here. And that particular year, I sort of went over the thermal exam, the thermodynamics exam. And so somewhere about the start of optics. Yeah, it says here, exam number 2, solutions and intro to optics. I'll send that. It's on the playlist. It's number 16 in that playlist. Control copy. Okay. Let me send that. But if you go to that one, the first like 50 minutes talks a little bit about the exam we did. I don't know how much depth it is. Sometimes I can go into much more depth. But anyways, those are the 3 things that were on my mind. Don's actually review, the actual practice tests that are on PDF and with the solutions on them, and then this video lecture that was from 2013. But those are the 3 that I do plan on sending to you guys. In fact, are you the one, Jake, who asked about a practice exam? Oh no, it looks like it was Ryan. So, yeah, thanks, Ryan. Yeah, and that kind of clued me in, and I saw that, and I was working towards it, and just hadn't got there. But I want to make sure I get that to you guys. And I guess today is later than I'd like, but well, better late than never, I guess. So, but your test is until Tuesday, so you still got a few days here to get this stuff digested.
Yeah, thank you.
Yeah. Okay, so yeah, good. So let me or even write that down as a note to me so I really don't forget it. Practice test. 3 items. Email that to you guys. So I'll make sure I get that done tonight, and hopefully even before all the Zoom's done, I can do maybe that on one of these breaks. And that way, like, when I put together the Zoom video here tonight with what we do, because I can think there's going to be a busy day as you guys are got a new deadline. All right, so let's go back to the chat here. All right, so Anthony, your number first here, and you've got, let's see, I'll put a time here, 10:10, and it's chapter 22, number 50. Oh, good. That sounds like a tough one here, way up there in the numbers. Oh, the next one is 51. All right. So, all right. And then we'll go back a chapter. Oh, good. Thank you, Daniel. You have some breathing room. Okay. All right. So let's me find my. Oh, and I do apologize again. I know what happened. It's just kind of sad that chapter 22, the 3 pages, apparently 2 of them or all the pages kind of stuck together. So it looks like there's only 1 page, and that only goes up to number 28. So it'd be on one of these missing ones. The second page, has the number 50 on it, or the first of the missing ones. All right. So let me read it. Looks like it's a pretty long one here. An athlete whose mass is 70.0 kilogram drinks 16 ounces, that's 553.6 grams of refrigerated water. The water is at a temperature of 35 degrees Fahrenheit. So they're gonna make me work a little bit here with the old English system here. All right, I'll switch that right away. A, ignoring the temperature change of the body that results from the water intake, so that the body, and that seems like a pretty good, reasonable approximation. The body's a big object. You're talking, 70 kilograms, mostly water, and you're only adding under a half a kilogram. So well under 1%, but there's probably some change. But anyways, ignoring the temperature change of the body that results from the water intake, so that the body is regulated as a reservoir of the 98.6 degree Fahrenheit, find the entropy increase of the entire system. Okay, so let me break this into 2 parts. Maybe I'll take a little chunk of water. So here is the water that starts at 35. Oh, and I started writing without sharing my screen. Hang on here. My bad. Let me finish setting up here. All right, here's the phone. Let me share it. Let me jump over here and connect. Yeah, maybe I'll grab my calculator while that's connecting. Okay, good. And good. All right. Looks like I'm sharing here. All right. So here's what I started to write. Maybe I'll just put here's page 1. Okay, so it's number 22 or chapter 22, number 50, in this water. And so this water is starting at 0 degrees Fahrenheit, and of course would then go into your body and warm up. And so they're saying 98.6 degrees Fahrenheit. Now let me change that into Celsius, just kind of get that out of the way right away. And let's see, I always have to think about this. Let's see, if I had the temperature on the Celsius scale, and since the Fahrenheit has 180 for every 100, because ice water to boiling water is 180 degrees on the Fahrenheit scale, but only 100 on the Celsius scale. And so the temperature on the Celsius scale is above ice water. So this would change it to how many divisions are above ice water. And then on the Fahrenheit scale, ice water is measured above 32. So I have an offset of 32. Okay. So this is the mathematical relationship between temperature on Celsius and temperature on Fahrenheit. So if I rearrange this, if I take the temperature on Fahrenheit and subtract 32, and then multiply by 100 over 180, I would get the temperature on the Celsius scale. All right, so let's see what that gives me. So 35 minus 32, then multiplied, and this actually reduces, I can divide by, well, if I divide by 10, I get 10 over 18. Divide that by 2, I get 5 over 9. Okay, so that reduces to 5 over 9. So 5 over 9, and that means we're starting at about 1.67 degrees Celsius and going to 98.6 minus 32. Get my laptop out of the way of my paper here. Okay. Minus 32. So that's 66.6 above ice water. And then multiply that by 5 over 9. We're looking at about 37 degrees Celsius. Now, since the question said something about entropy, okay, so let me come back where the question. Yeah, find the entropy increase. That needs to be in Kelvin. So let me do a conversion to Kelvin. And so it's 273. Maybe I don't need a calculator for that. But this would be then 274.67 Kelvin. And then 273, that would make a 10, carry 1, makes 11, carry 1, 310. All right. So I think this is what I'm going to care about here as far as the calculations, the absolute change in the temperature. Okay. And of course, the question says find the change in entropy of everything. And so that would be the water and the human body of this athlete. But let me just start with the water here. But because the formula to remember is a calculus one that says the change in entropy, a small infinitesimal amount of entropy change, is equal to this. It's related to the heat energy and the current temperature of that process. So if you integrate both sides, this then becomes the change of entropy. And this side, we have to do an integral, which would be really easy if temperature was constant, and it's not. So why don't I do this? I'll leave the temperature in there, but I'll also go back, and I guess this would be chapter 19, and remind myself when I'm warming up a liquid, there is a connection between the heat energy and the change in temperature. So if I did this in terms of calculus, if I did a microscopic amount, I would say a microscopic or infinitesimal amount of temperature change would correspond to an infinitesimal amount of heat energy. So starting with the definition of our entropy change, I can then put that with an mc/dt. And so again, if my focus right now is just on that water that is being drunk by the athlete, the m and the c, these are constants. This is the mass of the water being drunk, and the c here, this is the specific heat of the water. So then I just have an integral of dt over t, and I'm going to be evaluating it from some initial to some final temperature. And unfortunately, that's a pretty easy integral to do. That's just the natural log of final temperature over initial temperature. Okay. Now, maybe I'll pause. The entropy is really kind of a measurement here of how much disorderedness is sometimes the way we like to say it. That's not the only way to describe it, but certainly one way to describe entropy. And given that our water is warming up, and given that warming up means the molecules move faster, this should have more of a randomness. So this should be a positive number. Let's see what it comes out to be here. If I take the mass to be the 453.6 grams, and I multiply by the specific heat of water, 4.186 joules for every gram for each degree Celsius or Kelvin that it changes, since a change in Celsius and a change in Kelvin are the same. And then I have the natural log, and the final temperature is the 310, and the starting temperature is 274.67. So, huh?
So the equation that you integrated for MC ln of TF over TI, I've done that a couple times in the homework. On a test, would we have to rederive it, or can we just write it down?
Oh, you could just write it down if you, yeah.
Okay.
Yeah. The thing though that I will warn you about, and it sounds like you got this, it only comes out to be this formula because we are talking about, this equation for the specific heat and the temperatures changing, because there are many other formulas for the change in entropy. They all come from this integral, but they don't always come out to be this.
Mm-hmm. Right.
Right. And you'll see that when I do the human body here in a second.
Okay.
Yeah. But I think you got that idea. Okay. So now if I grab the calculator here, I could put my 453.6, multiply it by 4.186, and multiply that by the natural log of 310 over 274.67, and hit enter. And this comes out to be 229.8 grams would cancel, and I would be left with joules per Kelvin. So sure enough, as I said, this is going to be a positive number. Now, with that positive number, let's take a look at the human body here, because the human body now is going to be a little different.
Yeah.
Oh, bummer. So soon. Okay. When does it do that? And thinking maybe I should get myself kind of a webcam with a USB interface. Wonder if that would make it more stable. Thinking so.
I think you might be able to connect it via a cable too. I
tried that, and then you took the USB cable and I put it in, and didn't seem to run the video. It still, when I wanted to connect, it still did the Bluetooth connection.
Maybe the cable just links it.
Yeah, no, you're right. And there probably is a way. I probably should experiment a little bit with that. I just tried it one time and I go, oh, that doesn't work. Okay.
If you got a USB camera, then you would just need a program that would show the camera on your screen, and then you could just share your screen from your laptop.
Right. And then and that's how all these, the USB cameras, have a software piece that shows the camera and the output of the camera. And then that's the one I use when I make your guys' labs and stuff, the video labs. It's the camera. I guess technically it's not a USB camera because technically it's a high definition, and then I got to feed it into a video card, capture card, but it converts it into USB, which, anyways. So, this is, maybe I should research the iPhone a little bit, because it seems like with the USB connection, it would have something. Okay, now the second part of this, and then what I mean by that is second part of A. We still have to do B, but here's what I've done is I've calculated the entropy, and it's a positive number of the warming of the water. Let's do the same thinking for the athlete. Maybe I should start without an integral. The definition of a infinitesimal change of entropy is an infinitesimal change in the energy over the temperature of it. So if you then integrate both sides, you would have the change in entropy. And under this integral, they're saying, let's just assume that the athlete doesn't change their temperature. And if that's the case, then we can pull it out in front of the integral, which makes the equation a little bit different, because then an integral of dq is just q. And so here is a second and different looking formula. And so let me go back to page 1 here. This seemed to be the appropriate formula for the water, but do not use it for the athlete. This is the appropriate. And that's what was my little warning that you seem to have, Anthony. So not so much for you, but anybody else listening to this right now or in the future, that it's really tempting to see just one equation, either this one or some of the other ones, and try to use it for all the cases. The best thing to do is to write it down in its integral or differential form and then integrate it based upon the conditions that you have. And in this case, since the temperature is not changing, I would do this for. And then also notice that the change in entropy will be positive or negative depending if Q is positive or negative. So if heat energy goes into the athlete, it is a positive, but if heat energy comes out of the athlete, it's negative. And that's what's happening here. The energy is coming out of the athlete and going into the water. That's why the water is warming up. And in fact, before I even try to do this calculation, I'm going to point out then that the sum of the Q's is 0, meaning according to conservation of energy, the energy going into the water is equal and opposite to the what I'll call Q2, the heat coming out of the athlete. So maybe underneath it, I'll put H2O, and maybe over here, I'll just put ATH for the athlete. And so what I really want is right there, what is the Q of the athlete? And so Q number 2, Q of the athlete is negative of the Q of the water. And of course, it goes into the water, so that's positive with a negative in front. It's going to give me a negative for Q2. So sure enough, energy is coming out of the athlete. Now, the water energy calculation, we'll go back to page 1, is this crazy thing here again. Go back to, I can't remember if that's chapter 19 or chapter 20. I want to say 20. But this here would be the MC delta T. And so putting that in, the mass of the water was the 453.6 grams. The specific heat of the water was 4.186 joules per gram for each degree Celsius or Kelvin. Maybe I'll just degree Celsius. And the change in temperature would be the final temperature of 37 degrees Celsius, starting at 1.67 degrees Celsius. And putting these then into my calculator, I'll do the 37 minus the 1.67. Okay, so there's the change in temperature on the Celsius scale and the change on the Kelvin for that matter too. And then times 4.186 times 453.6, coming out to be a negative, looks like 67,080, I'll round it up to 4. And then grams would cancel, degrees Celsius would cancel, and joules. Okay, so now I can do the change of entropy of the athlete, the minus 67,084 joules divided by the temperature of the athlete, which in Kelvin is 310 Kelvin. So taking that and divide it by 310, I get a change of 216.4 joules. Oh, negative, sorry, negative. And that, of course, makes sense because the athlete is losing thermal energy. So decrease in entropy. Now, we can finish this by getting the change of entropy total by saying, okay, what is the change of entropy now of the water added to the change of entropy in the athlete? So the water, we said, was 229.8 joules per Kelvin. And the athlete, we just said, was a negative 216.4 joules Kelvin. And so 229.8 minus 216.4 gives me a positive of 13.4 joule Kelvin. And the fact that it's positive, hopefully it's not a surprise. That was the whole second law of thermodynamics, that when you have any process happening here, the total change of entropy, when you include everything, will always be greater than or equal to 0. So sure enough, this warming up of the water and the cooling down of the athlete has a change of entropy that is slightly positive. And I suppose, it looks like there's a part B here, so maybe I'll hold off here. And I was going to see if I did that right, but I'll try part B next here and say, all right, what is part B trying to say here? And I need to read it. Part B says, what if? Now assume that the entire body is cooled. Okay, so this time we're going to let the body change by the drink, and that the average specific heat of the person is equal to the specific heat of liquid water. Oh, okay. So they're going to say treat the body as if it is all water. It is mostly water, but the average will come out be roughly the same as water. Ignore any other energy transfers by heat or, of course, any adding of heat through your metabolical processes, okay? Find the athlete's temperature after she drinks the cold water, given that the initial body temperature is this 98.6. And under these assumptions, what is the change of entropy? What is the entropy increase of the entire system? Okay, so B is a little different in the sense that we still have our cold water that's going to be ingested or mixed with a big object. This will be the athlete. But unlike A, where they're saying just assume that the athlete keeps the same temperature, they're saying actually let the athlete's temperature drop a little bit. And probably reality is somewhere in between, because there's going to be this metabolic rate that's going to keep the body temperature up. But there's also going to be a cooling down. It's going to take a little while for that to happen. But anyway, so I kind of like what they're doing here, but it also gives you a chance to kind of redo this problem. So essentially we're redoing the problem. We're finding the change in entropy. The change of entropy of the water, though, would be that same type of integral. It would be an integral of dq over t. And as you said, Anthony, you've done this a lot. So do we have to do this integral again? And I'd say no. If you just want to start with mc natural log of final temperature over initial, that's fine. However, what is important here to recognize is that in part B, the final temperature is not going to be the 310 Kelvin like it was in part A, that the athlete's going to cool down. Now, we're still going to start at a temperature of, what was it, 200? Excuse me. 274.1. No, what was it? Let me find it here. It was back on page 1. 274.67. Let me take a little drink here. And a little cough there. Something caught in my throat. All right. So I'm still going to start with the water at that temperature. The thing, though, that's going to change here in part B is we're not going to have a final temperature warming up to the athlete, because the athlete's going to be cooling down and need it down a little bit. Probably not much, because the athlete is huge compared to the water. So there's not going to be much of a drop in temperature. But that's where I guess I need to start then. I need to go back to the sum of the Q's and say they're equaling 0. That is, heat comes out of the athlete and goes into the water. So I have this Q1 and this Q2, and that has to equal 0, where Q1 is the water and Q2 is the athlete. So the water would be this MC delta T for the water. And now the athlete Q is actually also going to be an MC delta T. We're going to be treating the athlete as a big 70 kilogram chunk of water. So if I put in right here the M for the water, the 453.6 grams, and then multiply it by the specific heat of 4.186 joules per gram for each degree Celsius. Then the water is going to go to some final temperature minus its initial temperature. Maybe I'll go ahead and do temperature in Kelvin. Why not? Because the initial temperature of the water is the 274.67 Kelvin. So maybe I should also write the specific heat in terms of Kelvin, not degree Celsius. The other term here, this would be the mass of the athlete. I have a decision to make here. I've been using grams, so maybe I'll stick to that. So this would be 70,000 grams for the mass of the athlete, and then 4.186 joules per gram for each change on the Kelvin scale. And then for the athlete, again, this would be a final temperature minus the initial temperature of our athlete. And I need to come back here to page 1. So our initial athlete, we decided, is starting at a temperature of 310 Kelvin. And all that has to equal 0. Maybe I'll save myself a little bit of work by just dividing every term by 4.186. And so that'll go away, and that'll still be equal to 0. Okay. Maybe the next thing I will do is divide by 453.6. 453.6. That's still going to get a 0 over here. But I like that because that just leaves me with final temperature minus 274.67 for my first term. And then my second term can be just written with a single number out in front. That would be 70,123,000 divided by 453.6. And that gives me 154.3. And then final temperature minus 310. And the reason I like that is because then I can just have a 1 here and a 154, which when I add 1 makes 455.3 for the putting the like terms together when I do the distributive property there. So that's kind of nice there. And then maybe I'll do the distributive property on this one. This is this 154.3 times 310. Oh, actually, it's times a negative. So that will be right here, negative 47,833. So then when I take that one, which is subtract 274.67, I get a negative 48,107.67 equals 0. Now, looks like I'm going to need yet another page to complete this. Just maybe in case I keep track, that's page 3. Okay, so now we're off to page 4. And so now I can just write final temperature, and I can move the 48,107.67 to the other side so it's positive, and then divide by the 155.3. So it looks like I already have that in my calculator, but with a negative sign. So I'll ignore the negative sign and then go 155.3, and I get 309.8. So this is kind of a fun comparison because in part A, without letting the athletes cool down, we said the final temperature of the athlete was 310. Now that we give the athlete a chance to cool down, but the athlete's so much bigger than the water she's drinking that it's only cooled down 0.2 degrees Celsius or 0.2 Kelvin. So there's not much of a cool down, as you can see. So the approximation we made for A seems like a very reasonable approximation. But like I said, reality is probably somewhere in between, because it's probably not even going to cool down this much because the metabolism is going to kick in more heat while she's drinking the water. Although she's probably going to lose a lot of heat due to perspiration and conduction and convection off the skin. Anyways, so maybe I should put Kelvin here. All right, so now we can get back to where we were, and let me jump back to page 3 here. So what we were saying here is you can calculate the change of entropy of the water, really kind of doing the same mechanism. And you're going to see there's going to be a small differences, but the final temperature is pretty close. So I kind of think we're going to get the same kind of change of entropy. But let me fill it out now. So the change of entropy here of the water would be this MC natural log final temperature over initial. So the mass is the 453
You froze again.
grams. Hey. I should touch my screen once in a while. I wonder if it's just that thinks it's going no activity or something.
There's a
No,
setting.
because it freezes. It doesn't just disconnect.
Okay.
I don't know. All right. Well, anyways, it's hunting again here. All right. We're back. Okay. Well, I guess the freezing's kind of motivating me to get that USB thing connected. All right. So let's see. Let me backtrack a little bit since it froze. But what I was trying to do was jump back to where we started B here on page 3, was that we have this little formula for the change of entropy. And it would be MC times the natural log of the ratio of the final temperatures. And now it's a little lower. Not much, but a little bit. So it's going to be very, very close to the same, but with a small effect. Okay, so the mass is this 453.6 grams. The specific heat is 4.186 joules per gram for each degree, or let's do Kelvin. And then the natural log, and I guess now we've decided that the final temperature is 309.8 Kelvin instead of 310, as it was in A. The initial is still the same, 274.67 Kelvin. And so Again, notice that's going to be a positive number, 453.6 times 4.186 times the natural log of 309.8 over 274.67. So this will be a positive 228.5. What did we get before? So coming back here to page 1, when we did A, we got 229.8. So now we got 228.5. Well, that's more of a change than I thought would happen. Changed by over 1. Okay. But I guess that's pretty small, really, in the scheme of things. We're way over 200, so a change of 1 is under 0.5%. Okay, so that's our change of entropy for the water. And by the way, notice it is positive because it's warming up, but also notice it's not as big as it was before because we're not warming quite as much. Before we went to 310. I should check. Did I do any other rounding? Did I use point? Yeah, I did. Okay. All right. But like I said, there is a difference, more than I would have guessed, but certainly not much. Now, the thing that changes more significantly in part B is the change of entropy of the athlete. See, the athlete is now actually changing her temperature. So when I do this integral dq over t, I can't make that statement that the temperature is a constant and I pull it out. Although you are seeing that the temperature really didn't change by much. So our approximation that we did in step A is not bad. But I'm going to then treat the athlete as if she's a big container of water. And so there's a change in temperature to this container. And so we would be using this formula for the athlete. And let me say it again for anybody listening to this and now or in the future, that this is a great formula, but don't use it in every case. We've seen it quite a few times in this first problem, but that's one, and we saw a second one, but those aren't the only two either. You know, there's a lot of other formulas for, where is that? Page 2. Yeah, so we had this other formula when we did it, treating the athlete as a constant temperature. But we have other things that, may come into play. Like none of this included a change in the volume if we had a gas. So that's a good question to ask. What's the change of entropy when the volume changes? Okay, but here then is the formula. Now I'm going to apply it to the athlete. So taking the mass to be 70,000 grams and the specific heat to be 4.186 joules per gram for each change on the Kelvin scale. Then I can go natural log. And so now the final temperature is this 309.8, and the initial temperature is the 310. So you can see we got a ratio less than 1. The natural log less than 1 is negative. And so sure enough, the change of entropy should be a negative number. And I would say that formula looks very, very different than the one we did here. Although since the temperature change is not much, I'm thinking that we should get a number that is negative and pretty close again to what we got before. And so let's see what we get here. Although last time when I said it was pretty close, and it had a change of more than 1, more than I anticipated. So let's see what we get here, this would be 3,000 times 4.186 times the natural log of 309.8 over 310. And so this is a negative 189.1 joules Kelvin. Yeah, and that is quite a big difference in consideration. We got negative 216 before. And again, figured it would be a negative, figured it'd be less. That much, a little surprise to me. So I'm going to make sure we check the solution guide here when we're done. So finally, the total change of entropy would again be the change of entropy of the water and the change of entropy of the athlete. So the water was right here, was a plus 228.5, and the athlete was a negative 189.1. So 228.5 minus 189.1, and we get a plus 39.4 joule Kelvin. When we do a different calculation, I was about to say better calculation, but I'm not so sure it's better. Maybe it is. Maybe I'll call that better. But the big thing is it's different. But we're letting the actual body cool down. And if the body really was a blob of water and had no metabolism, this would be a better calculation. Sure. Now, let me jump over here to the solution, because, like I said, things went in the right direction, but a little bigger than I would have guessed. Scroll all the way down to number 50. All right, so in 50, part A, they got a total change of, I'm looking at the wrong one. Okay. Okay, wait, 50. Oh, they still got a different number back in A.
I think they used calories for Kelvin instead of joules.
Thank you. Yes, I do see that. So they used calories. So let me take their answer. They got 3.19, and let me multiply by 4.186, and they're getting 13.4. Good. All right, so we agree. They just, like you said, yeah, they did a different unit system. So thank you. I didn't notice that. So okay, so we agree with A, and then in B, they got 2.59, but again, they got calories. So let me convert that to joules, 4.186. So they're looking, they only, okay. Okay, wait. I think I might have a little mistake here. Let me check my water. They got for their water 54.52 in calories. So if I convert it, they get 228.2. Okay. But this seems to be different. Oh. And it's really going to be right here. They got a 309.92. So let me go back to part B, where I tried to calculate.
It also looks like they used a different initial than the 310 on the bottom.
Oh yeah, they used and they used 310.15. Ah, getting some kind of spam call. Get rid of that. Ah, okay. Yeah, and this is very, very sensitive to small changes. I think it's going to come back. Let me just check this out. But when I turned to Kelvin, I added 273. But a little more accurate is 273.15. And so that would make my final temperature 300 or my initial 310.15. And then that's going to explain why we are a tenth and a little bit different on the final temperature. Okay. Well, let me just say that they probably did it a little more accurate, and I should have too. But I'm not sure, unless you guys want me to, there's much value in going back and changing every number. But yeah, it really comes back to right here on this conversion on page 1. I should have gone 1.67 and added 273.1. Five or 1.3. So this really should have been a 274.82. And then that would make this 37 plus 273.15. And that would mean it would be 310.15. Ah. Okay, so these extra decimal places would matter when we're talking about the body only cooling by a tenth or 2/10 of a degree. You're going to get some slightly different numbers. So, I'm not going to.
Is it close enough to your liking though?
Yeah. So I guess what I'm trying to say is my logic is sound. I probably did too much rounding, and that's why it shows up different. Bummer. Wish I wouldn't have rounded that much. It would have looked better, but the logic is there. So hopefully you got that information from it. And by the way, if that had been an exam, I have no problem with these different numbers. That's happened in the past where I'd look at some student's problem and go, hey, everything looks so good and their number is different than mine. And then I looked at the rounding and usually you don't expect that much difference, but it depends where and how the rounding is. And then this one does matter. So I shouldn't have rounded my 273.15. I should have left it at 273.15 instead of just rounded 273. But I didn't realize this small change. I guess I should have read part B before I did part A, and then I would have realized that hey, this is only going to be a small change. All right. Well, I hope that was helpful. That was a good problem, long problem. Let me set up then. Unless you guys have a question on that one. For the second one that you guys were asking.
I have a quick question.
Yeah.
I'm just curious, on the exam, should we be prepared to find specific heats of different materials using that chart in the book? Or will it?
Yeah. Yes. So remember the test is open book, and you'll need this material has a lot of what we call measured parameters. So specific heats are one of them. Latent heats are another. Thermal expansions are another. And so, yeah, you should know that your thermal expansion numbers are in chapter 19. Your specific heats and your latent heats of fusion and vaporization are in chapter 20. Of course, it's also open book, so you could kind of Google anything.
Okay, cool. Thank you.
When we're doing those problems on the exam, does it matter if we like use like calories or joules when we're dealing with like specific heats and stuff, or as long as we use the right approach, are we good?
Yeah, the right approach is good. Unit, it's the same thing of, do you finish a problem and give a distance in meters or centimeters or millimeters? It's just a conversion factor. So unless the problem specifically says, you can do whatever you want.
Sounds good.
And I was tempted to use calories. I kind of like them, but that's kind of old school. And I go, well, I'm sure the book does joules. So I went ahead and did joules only to get to the answer and see it in calories. Like, oh, hey, whoa, that took me off guard. Yeah.
In chapter 21, I noticed we have to use the molar mass a lot. So on the test,
Oh, yeah.
would you give us the molar mass?
Again, probably not, because again, you have your textbook, and so they're all listed there in the appendix. Right in your appendix is a huge periodic table, and so besides knowing the tables that are in chapters 19 and 20, know that you have a giant periodic table. I think it's appendix A. Could be B. No, B is where they do all the math review. Oh, now I want to say D. Well, you know what? I'm going to look it up. But I'll scroll down here to the bottom of the PDF. Appendix A says tables. Periodic table of elements. Appendix C. Yeah. Pretty simple one, but it does give the atomic number, the atomic mass, the symbol, and even the electron orbital configuration. So it's not a real complicated, but it does give the molar masses. So, yeah. All right. So now let me jump back to the Zoom. I'll go to the next question unless you guys have more on this, but I'll also use this as an opportunity for you 102 people. I want to work you guys in first. These are long problems. So if anybody's there in 102, it looks like a lot more people came in. Speak up. Is that you, Claire?
So yes, hi.
Hi.
I'm in Folsom's 101. Oh wait, did you say 102 or 121?
Yeah, I said 102.
Okay, I'm actually in 121. So.
Hey, go ahead and throw it in the chat. Maybe.
Okay. Just type it out in there.
Yeah. Type it in there, and I'll do yours next. Hopefully that won't aggravate too many of my other ones who are already in there. But you guys have preference at the second one, anyways, at 12:30. So I take you guys first at 12:30.
Oh, I see. Okay, thank you.
But okay. All right. So with that said, that was a big one. Let's try now. Oh, another big one, number 51. I think it's the one right after that. Okay, so chapter 22, number 51, and the time is 11:08. And let's see, it must be just below this. Okay, this looks like a lot shorter one. We'll find out here in a second. So all right, here at the top for anybody kind of scanning the video, chapter 22, number 51. And it says here, a power plant having a Carnot efficiency produces 1,000 megawatts of electrical power from turbines that take in steam at 500 Kelvin and eject it water at 300 Kelvin into a flowing river. The water downstream has warmed up by 6 Kelvin due to the output of the power plant. Determine the flow rate of the river. Okay, so these heat engines, we kind of design them. Well, there's two ways we do it. One is the actual mechanical design of it. Like an internal combustion engine, you have the pistons. Another way is what we just call the thermodynamics approach. And we just say, look, you put heat energy in, so we call this QH, and then through some kind of gearing or mechanisms, or the case of an internal, well, this says turbine. So I guess in case of a turbine, we have this expanding gases that are pushing on these blades. It's going to do work. And then some heat energy exits the engine. And the principle of conservation of energy simply says this, that what goes into the engine, so heat engine in, equals to the energy that comes out. And so what comes out is some of the energy as heat and some of it is work. Now we do have to be a little careful with our signs because we've been saying energy coming out as a negative number. So let me just, emphasize that I'm thinking of the heat coming out as a positive number. So this is the energy coming out. This has to equal the energy going in. Now, the beginning part of this says it is operating with a Carnot efficiency. And so hopefully one of the lessons you're beginning to get out of this heat engine process is that there is a particular cycle that is very, very slow, but is a good one to study. It's called the Carnot cycle. And Carnot was able to show that you cannot have an efficiency better than this because this is the best you can do and still be within the first and second law of thermodynamics. And the reality is none of our engines actually run on a Carnot cycle. They just run too slow. And so they all actually run with a little bit lower efficiency than the Carnot cycle. However, the Carnot cycle is one that academically is good to talk about because it gives us a goal. It gives us something to shoot for, okay? So without showing that, because that was kind of the lecture, I'll put E sub C for the Carnot efficiency. And there was a part of the lecture, was also done in example number 3 of the book, and I suppose I could repeat it here if you want, but in order to attack this problem, let me just jump right to the formula that says in a Carnot cycle, this would be the efficiency of that engine. So the efficiency of this power plant, because they say it's operating on a Carnot cycle, and I'll say it again, it probably is not. That's probably not reality. They're trying to build some cycle that is close to the same efficiency as the Carnot cycle. But in this case, the cold temperature is 300 and the hot temperature is 500. So this is really 1 minus 3/5, which of course is 2/5, which is 40%. So they are saying that if you're going to operate a heat engine, in this case, it sounded like it was a power plant, and it sounded like it was steam. Okay, so they're using steam turbines here. They're operating at 40%. And let me emphasize, 40% sounds terrible. And I guess it is. But keep in mind, that's perfection. And that's really what needs to be emphasized. People really miss the second law of thermodynamics. They just see the 40%. They see the first law. They say, wow, we're wasting 60%. And I would say, well, we're not wasting it. This is what nature is saying the best we can do. So if you are actually achieving 40% of this power plant, you are doing the best Mother Nature will allow you to do. End of story. Now, these temperatures are kind of low. So actually 40% efficiency is typically an internal combustion engine these days. So they're actually getting really good. But that's still far from their Carnot cycle. They got a lot of room for improvement. But never shoot for 100%. That's my whole point. 100% is not allowable when you factor in the second law of thermodynamics. And that, I guess, because the second law of thermodynamics is probably the hardest one. It's the one that people just forget about. Yeah, I'm not going to pay any attention to it. I'll just think about the first law, and I'll think just about the energy. Anyway, so this power plant is actually operating in a Carnot cycle, the best it can do under these conditions, and we are at 40%. Okay, now here's what the efficiency means. The efficiency means that you get 40%, so the work out compared to the heat that you put in. And the reason that is important is I could now solve for how much heat energy is going into my steam turbines. You see, I know that the efficiency is 40%, okay? And I know the work coming out because it says very clearly in the problem, it produces 1,000 megawatts. Now maybe just for completeness, I should have made one more step. Let me do something here. If I divide the numerator by time and I divide the denominator by time, you might say I kind of have the same thing, and I kind of do. So that's why I was kind of overlooking it. But this would be the power out compared to the power in, while this is the energy out compared to the energy. But they're still the same ratios. So that's really what I should have done before I started putting in my numbers, because what they're telling me is the power coming out. They're telling me this is 1,000 megawatts coming out. And so I can solve for the amount of heat energy per time going in. And so the heat per time going in would be 1,000 megawatts divided by 0.4. So if I take 1,000 and divide it by 0.4, we are looking at 2,500 megawatts. So 2,500 million joules per second of heat energy go into this power plant. And in that process, 40% of it looks like it gets converted into work or electrical energy. They say power plant. I know. They say electrical? Yeah, they do say electrical power. Okay. So they make electrical power here in this power plant. So again, they send in a lot of energy, 2,500 megawatts. And what comes out of it is 1,000 megawatts of electricity, which then means the rate at which the cold is coming out. And so let me come back here to the first law of thermodynamics, right? It's saying the cold plus the work have to equal the hot. That's our conservation of energy. So if this right here, and maybe I should, for a little more completeness, divide by time, okay? So cold energy per time, work energy per time. So if I know that this is 2,500 and I know this is 1,000, that means this must be 1,500 megawatts. So this power plant is using the water in the river to cool it, and it is dumping 1,500 megawatts of power or energy, heat energy, into the river, which is why it's warming up. Okay, so I'll call that page 1. That's the part that's relevant for chapter 22 as we discuss the operation of a heat engine, and in this case, the hot steam going in to expand and push a turbine blade, or turbine blades, by many of them with this much power. That's 1 gigawatt. That's half the size of Hoover Dam right there. And so we're going to then be saying then that the river now is going to be warming up. So let's talk about warming up water again. So here's how we need to go back to chapter 20 and say Q equals to MC delta T. If you have a certain mass of water and a specific heat of water, and it'll change its temperature according to how much heat there is. Now, if I divide it by time, then this side right here, this is the Q per time. This is the 1,500 megawatts. This is the amount of thermal energy that is being dumped, I guess. I don't know if I want to use dump, almost sounds mechanical. So ejected, I don't know what word I want to put there, but this is the amount of energy per time, heat energy that's going into the river. Okay, so this is what's going into the river. Let me need the mass per time alone, because that's really the question. The question here is determine the flow rate of the river. How much water per time? How much water is flowing per time? So then this is 4,186 joules per kilogram. Notice I didn't put the point here. I'm going to do things in kilograms, because notice I got watts, and a watts is a joule, and a joule has a kilogram. So this is 4,186 joules per kilogram for each degree Celsius or Kelvin that it warms up, because they're saying it warms up by 6 Kelvin. Now, maybe I'll just play with my units here. Maybe over here, I'm going to write this as 1,500 times 10 to the 6th, and this watt would be a joule per second. Because then the joules would cancel off. Kelvin would cancel off. When I move this over to here, it will be kilograms per second. Yeah, so kilograms per second is going to be my mass per time. Okay, so I want to solve for mass per time. All right. So over here, grabbing my calculator, I have my 1,500 times 10 to the 6th. And I'm going to divide it then by 4,186. And I'm going to divide that by 6. And I get 59,720, I'll round it to a 3, kilograms per second. Now, maybe I'll check my answer, but I almost want to put this in a volume. And I know that there is 1,000 kilograms in a cubic meter when I deal with the density of water. If I divide that by 1,000, we're looking at 59,000.7 cubic meters a second for the, I'll call it the volume flow rate. And all they said determine the flow. So I could see them listing it in either kilograms or in volume. So, but I guess I'll find out here in a second here. So 51, they got 59,700 kilograms per second. So they left it there. They didn't do volume. So good. Nice. All right, Claire, then I'm going to jump back. I know there's a bunch more for you guys in 123, but forgive me. I'll just kind of move her up and take a little break from 123 for a second since we've done so much. And
Thank you. Sorry to cut in line like that. I thought I mixed up the times. I thought this was the last one.
Yeah, no worries at all here. So let me write down. What are you're saying? It says I had a conceptual question.
Yeah, I have a couple conceptual questions about
Okay, good.
like the work equations as a whole. So I guess my first question is, when we're deriving the work kinetic energy equation, which I understand the derivation fine, but there's a point we cancel out the time differentials, dt. That's like one of the steps in the derivation. When you substitute in for, it's like you sub in dv dt for acceleration, and you do a couple things. Yeah.
Okay. Now I see what you're saying. Yeah. Go ahead. Yeah.
Sorry, I realize I'm referencing like a third step in a derivation without showing it, which is probably annoying. But basically, what I'm wondering is, I understand that we're just integrating with respect to position after that point, but I'm wondering what exactly we're doing by canceling the differentials. Like, I know algebraically, like, yeah, okay, you're canceling it, but is that like a change in variables, or like what are we doing?
Yeah. Change of variables is a good phrase. I think here's what you're talking about. If you start with Newton's second law, F equals ma, and then you try to convert it to work by saying, I'm going to integrate with respect to distance, and I'm going to keep it simple and just call x the distance, if that's okay.
Oh yeah.
And so if I multiply both sides by a small distance, dx, and then integrate, the left-hand side, this is our definition of work. And then what I think you're referring to is then doing this integral, we could replace acceleration with dv dt. Now, you mentioned canceling out a dt. That's what kind of threw me off, because what I usually do then is combine these two together.
Oh, interesting.
And that becomes dx dt is v. And that process changed what you said, the variable. I changed it from an integral of dx to an integral of dv.
Okay, I see. So I think it's the exact same thing. I think just in the derivation I was looking at, they replace dv, or they replace dx with dv dt, or dv times dt.
Okay.
So I think it's the same. Oh.
And I kind of got the impression that your question was justifying doing this. So,
yeah, I guess I was just wondering if it was considered like a change in variables? Because
Yeah, I would just call it a change in variable because of this. Let me write it out in its longer form. Remember that a derivative is the limits as, delta t goes to 0 over delta v over delta t. So that really is dv dt. It's actually just a quotient. So if you are going to actually then multiply by a delta x here, you can just regroup things and put your delta x over your delta t and take the limits, leaving your dv by itself. So I'm not doing anything more than if I told you you had something like 5 over 4 multiplied by 3, you could rearrange that and write it as 3 over 4 times 5.
I see. That's much clearer.
Okay, good.
Yeah, that's good.
And of course, the result really is, as you said, a change of variable, because all of a sudden now, instead of having an integral with respect to x, by regrouping the x with the t and then calling it a v, then I just have an integral of dv. And then that's where you get, when you integrate v dv, you get v squared over 2. And then your limits would be from some initial speed to some final speed. So you would have 1/2 mv final squared minus 1/2 m initial squared.
I see. Okay, that's perfect. I feel like I had a second. Oh, okay. So I have a second question about the same equation.
Sure.
Just really quickly. So for when there's a constant force,
Uh-huh.
I know the equation's a little different and there's a cosine involved. Is that, I just don't understand where it comes from, I guess.
Okay.
It's like work is force dotted with distance times cosine of theta.
Right.
Sure.
Okay. So I cheated you a little bit.
It's
in
a
this.
special case, right? Like there's a more general.
Yeah, right. So this is a special case where what I've done is just moved in the x direction.
Oh, okay. That's what I thought it was, but I was not sure. Okay, that
Yeah,
makes
okay. Which means then I'm talking about the force really in the x direction.
Mm-hmm.
So you're asking a I'll call it a better question. You're asking a question. Well, what if you had something like this? Or what if you had this box that, okay, the box is going to slide along. Oh, let's just say here's the floor. Okay.
Mm-hmm.
And so let's just call that the x direction. So it is going to move along the x, but because somebody maybe is taller than the box, they end up pulling it kind of up, and so they're pulling it kind of up and towards them. So what that would mean back here is, since we only want the x components, if this is this angle theta, and I start doing my vectors again, and you did the vectors when you did projectile motion,
Mm-hmm.
this would say that if you were to break this force down into how much of the force is in the x direction, you would say something like this. You would say cosine of theta is the force in the x direction divided by the total force. or move the total force over to here, you would say total force times cosine theta is really how much force is in that x direction. So if I come back to this first one where I kind of cheated you and I just said the force, this really should be the force times cosine theta, then the dx, then the integral of m a dx.
Okay, that helps a lot. And then I guess last bit on this one. The formula that I was sort of given was work is force dotted with displacement dot cosine theta. So there's no integration for that one, I thought.
Okay, good. Okay, now same thing though. You're blending together, and it's probably my fault actually, not yours at all. Special cases versus the general case.
Okay, I see.
So let me start with what you said, a dot. To save us from writing, instead of putting cosine in here, we like to write F and put a little vector, put a dot, and then to be a little more general, say that it's dr.
Oh, okay, I see.
Because boxes don't always move in the x direction.
Mm-hmm.
And so by calling it an r, we're leaving ourselves open to saying, well, in this case, does it move in the x direction? And if it does, then you just change the dr to a dx.
I see.
But
think in my journal I had an X there.
And if the box moves in the y direction, then we change the dr to a dy.
I see.
In fact, some of the harder problems is when the box moves in a curved path where the dr then would represent that curve. So it's not an x or a y axis. And it comes a little bit harder.
Mm-hmm.
So what I'm trying to say is this, what I'm writing now, is the more general formula. The dot means that you have to put a cosine of the angle between the force and the direction it moves.
I see.
And that's why we like that R. And I guess I should even check your OpenStax book if they use an R or an X, but I bet they use an R because.
Yeah, they definitely use an R at one point. I think I might have put the X in there on my my own autonomy and tripped myself up.
Well, see, yeah, and that's what I'm getting at. That's a special case, and I would say, why not? I mean, if the box goes in a straight line, call that the x-axis, and then the R just becomes an X.
Right.
And you'll feel more comfortable with that. But we like to leave it at a general form because sometimes the boxes move in the Y direction, and sometimes they move along an arc. Mm-hmm. And so we just need something to describe the direction the box moves and have it being separate from an X or a Y axis.
I see.
But and then the dot is there because we always want to say that you have to multiply it by cosine of some angle. But the angle is not from the x-axis unless the box moves in the x-axis.
Of course.
The angle is between the force and the direction the box moves.
That helps a lot. That's
okay.
Exactly where
now watch this for a moment.
Mm-hmm.
Let's just say that the force and the angle are constant. In other words, if I were to write this as force cosine theta dr, but the force doesn't change, I can pull it in front of the integral. If the angle doesn't change, I can pull that in front of the integral. And then I just have an integral of dr, which I probably should just write as r. And as long as I'm writing it r, I might as well go back to writing it with a dot. I might as well write it as f dot r without an integral.
I see. So that's
And
why.
this is, I thought I heard you say somewhere in this conversation that work was force dot r. And I would say, well, that is a special case. Did you notice that that only worked if the force and the angle didn't change?
Yeah.
So your best general case is right here with the integral.
And just go from there.
And start from there. But I must say that there are many, many, many times that the force is a constant, the angle is a constant. And so this you will see and use many, many times. But it technically is a special case.
I see.
And just like another special case is where a lot of times the object moves, and we just call it the d direction, and the force is in the same direction it moved. So the angle 0 and cosine of 0 is 1. And so you'll often see this equation, force times distance for work. But again, it's a special case. And it's probably one that you saw in your, I don't know where you took your pre-physics before 121, if you did 102 or if you
I did
did high
102.
school.
I did the 102 course.
Okay, that's what I was thinking. I thought I recognized your name from 102.
Mhm.
Did you have 102 last?
Yeah, I think I was in yours.
Yeah.
It was a
Okay.
good course. I really liked it.
Oh, good. Well, I'm glad you liked it, and glad it could. Hopefully, it was helpful even in this pandemic world we live in.
Definitely, yeah.
Anyways, but I know in 102 I do a lot of this. I do force times distance, and we do this over and over again. But it really is a special case. And now that you get into 121, we expand on it to the more general case, so that you can do harder, more complicated stuff and more realistic stuff.
Right. That makes a lot more sense. I think my downfall was putting an X there arbitrarily and reading it as such.
Yeah.
Okay, perfect. Well, that was my question. Thanks for letting me cut in line. I'll definitely come back at 12:30 next time.
Okay. No worries. Yeah. Well, we're probably gonna take a break right here and come back at 12:30. Yeah.
Okay. Thank you so much.
All right. You bet. All right, that was good. Let me write that down. Conceptual questions on work and energy. Okay, so I can put that on the Zoom one. And we didn't get too far. What did we do? We got two big ones going down. I'm going to write this down for you. Let's see. It would be Daniel next, chapter 21.
So we'll just continue in the next one.
Yeah.
Okay.
And
Sounds
then
good.
Jake, chapter 19, number 41. Okay. And then Andrew, 22, number 51. Oh, that's the one we just did. Oh, I guess Ryan and Andrew asked the same one. Okay. All right. So I'm glad we did that one. And then that's my link. And then somebody else, Hunter, you asked chapter 21, number 46. And then mine, and then Claire. Okay. Oh, good. So we've got 3 already for after our break.
All right. See you in a little bit.
All right, guys. We'll see you in a little bit. Take care.